So yesterday in class, we started out looking at phase diagrams where we could look at how temperature and pressure affects the state of matter and what conditions we can put material under to go through phase changes, such as melting, freezing, vaporization, and condensation. We identified where the critical point and triple point is found, and so we're going to continue looking at phase changes and looking at the heat and involved in making a change happen, whether it be an endothermic or an exothermic change. Yesterday we also identified our 6 phase changes that we have. Again, 3 of which are endothermic, 3 are exothermic. Remember, the word endo means that heat had to be absorbed. Exo means heat had to be released. Again, if you think about what it means to be a solid versus a liquid versus a gas, the particle motion helps decide if that was an endo versus an exothermic change. So to start out with our new topic, when we take a look at phase changes, a phase change happens at a constant temperature, and we're going to be looking at that through a lab next week where we can identify a material's melting point based on the data we collect, where we can get these plateaus in a graph or a constant temperature. And so if you took physical science or back in your days of maybe middle school, you probably encountered the word kinetic energy. So when we talk about motion of particles, what it means to be a solid, liquid, gas, solids have the lowest amount of kinetic energy versus a gas having the most kinetic energy. Kinetic just means energy of motion. So again, if you think back to first semester, we saw through the PhET simulation that a solid is very rigid, there's very little motion taking place, liquids have a little bit more, and again, gases have the most. And so during a phase change, when it goes through melting, freezing, vaporization, condensation, sublimation, or deposition, the amount of motion energy stays the same. What starts to happen is it starts to store that energy, and then it can go through the change. Again, a phase change can either have 2 options. You can either add heat to the system or you can remove heat. When you add heat, that allows molecules to move further apart because they have more energy, and that's where we get the phase changes where you move into the liquid state or the gas state. You can take energy out of the system. That slows down the particles. It removes kinetic energy, so they start to move closer and closer together, and that's where you can move into the liquid state or the solid state. What's happening is because of those flat plateaus in our graph where we get constant temperature, that's due to what's called intermolecular forces. So we've talked about intramolecular forces already. Intramolecular forces are bonds. So we talked about covalent bonds, the 2 types being polar and nonpolar, and ionic bonds. We're going to get into intermolecular forces later on this week or maybe early next week. We'll see how things go. So intermolecular forces are forces that are acting between molecules. So in water, for example, we have bonds holding the oxygen and hydrogen atoms together. Those are intramolecular forces. Intermolecular forces are forces that kind of help collect a water bonding to another water, and these forces decide how quickly a phase change takes place. And like I said, we'll get into those more next week. What we're looking at today is another graph, similar in that we're talking about temperature, but we're not looking at how pressure impacts phase today. We're looking at basically heat or time is usually on the x-axis. What we really care about is what's on the y, which is temperature. And so this shows where phase changes are taking place. We can figure out what a boiling point or melting point is for a material, and we can determine if you have a material at a certain temperature, what state of matter to find it in. Again, just a quick recap. There's 2 forms of energy we're going to talk about today, one being potential, the other being kinetic. Potential energy is stored energy. So for example, as you are digesting your lunch, you are breaking the chemical bonds apart in that. that was stored energy that you can then turn into kinetic energy to, say, walk. So potential energy is stored energy. During phase changes, this is when this increases because of those intermolecular forces. Kinetic energy, the motion energy of the actual atoms or molecules moving around, these increase when temperature increase, or vice versa, decrease when the temperature decreases. Another term, we covered these briefly at the beginning of the year when we worked on matter. Just to kind of recap, temperature and heat are not the same thing. Heat is a form of energy, and so heat can cause two things when looking at a heating or cooling curve. Heat can allow a material to change phase, or it can make the material change its temperature. One thing we'll notice is with phase changes, boiling requires more energy than to melt something. If you think about the shape or arrangement of atoms in something that's solid, they're very packed together, liquid a little bit more disorganized, and gases are spread very, very far apart. So it takes a lot of heat or energy to get those atoms moving faster and to move far apart. So we'll notice that energy is going to differ on boiling something or vaporizing versus what it takes to melt something. Temperature, on the other hand, is what we do to measure that energy. So temperature, we talked about 3 scales early on this year. We had Fahrenheit, Celsius, and Kelvin. We're going to be seeing a lot of Celsius and Kelvin here in the upcoming few weeks. When you measure the temperature of something with a thermometer, you are measuring the kinetic energy or the speed of those molecules. So when it collides when those particles, say water, collide with your thermometer that you're measuring it with, you are essentially measuring how much energy that water has as you boil it, for example. So let's go ahead and take a look at our heating and cooling curves. So the first thing I need you to do, because the table we're going to fill in talks about segments, this particular graph, this didn't label for us. We need to just label a couple of points. So what I need you to do is mark down here by the origin as A. We're going to label this as B, C, D, E, and F. So we're going to talk about 5 things at these segments. There's 5 segments going from 0 to 100 kilojoules of heat put in, and we can see the temperature at which this material changed. We call this a heating curve. Notice it has a positive slope overall. Again, you can tell it's heating because the temperature increases. So that's a pretty easy way to tell which curve you're looking at. So again, we're going to be able to interpret 5 things about it. We'll be able to determine what state of matter is in that segment, what's happening to delta T. We talked about delta T before. Remember, delta, that triangle just means change in. So how is the temperature changing? We're going to look at how the kinetic and potential energy change, and then ultimately if a phase change is taking place there. So to start out, this first segment is the segment AB that it's talking about. If we look at our graph, we have AB starting out our graph right here. So we can see it ranges from a temperature of 40 to approximately 60 degrees Celsius. If you think about water, what do we find at the lowest temperature range for water? We find the solid state, and that's true for any material. The lower end of the spectrum is where solids are going to be found. So the state of matter found in segment AB is going to be solid. If you take a look at your y-axis, which is temperature, what's happening to the delta T, we can see that it is increasing. So I'm just going to draw an arrow up indicating that temperature is increasing. So then we can talk about what is happening to kinetic and potential energy. Remember, kinetic energy is motion. Potential energy is stored. So because the temperature is increasing for this segment, that means our particles of whatever this material is that we're talking about here is going to increase. So that means kinetic energy is going to increase as well. So wherever the temperature is increasing, that means motion energy is going to increase. At this time, as it's heating, it's not storing any of that energy. It's using all of it to just increase the temperature. And when we measure that increase in temperature, it's because we are increasing motion energy. So I'm just going to draw a dash here to indicate there is no change in the stored energy. It's all solid at this point. Again, wherever you have slopes in your graph is where you have the same state of matter. We'll see in the next segment a plateau. That is where we find phase changes. So phase change, there is none. Moving to the next segment, we have segment BC. So again, we can see a plateau. So like I mentioned before, there's these intermolecular forces that occur between molecules or atoms within that material. Again, we can just use water, for example. So at this time, the temperature you can see is constant or stationary, that the temperature is remaining the same. So at this point, we're now entering a phase change. So this is where our solid liquid phase is found. So as we're going through a phase change here. So what's the delta T? It's going to be a dash. No temperature change is happening here. So because the temperature is remaining the same, that means our particles are not moving any faster, so kinetic energy is constant as well. Potential energy, so this is where it's starting to store that energy, so potential energy is going to increase here. And that will then be used to then enter the next segment, to go through, enter our next phase, I should say. So what do we call solid changing to a liquid? That phase change is melting. Moving into the next segment, CD, we can see we are back to having a line with a slope. At this point, all of that stored energy has converted our material over from a solid liquid blend all the way over to being just liquid at this point. Delta T, we can see it rises quickly from 60 to 120 degrees Celsius, so it increases. What happens to its kinetic energy? Well, its temperature increase, therefore its motion energy is going to increase. What about its potential energy? What about its stored energy? Again, it's moving faster, so nothing's being stored at this point, and it's all in the liquid state, so no phase change is taking place. We can see we're back to our next plateau, so we can see that another phase change is happening. So wherever you have plateaus, where it flattens out, you'll have phase change taking place. So temperature is increasing, so this means we're on the transition from liquid to the gas state. What's delta T doing? Nothing. It's remaining constant at 120. Kinetic energy, because temperature is not increasing, it's not moving any faster. However, stored energy, it's going to be storing a lot of this energy at this point. What do we call liquid changing to a gas? This is called vaporization. And specifically, the type of vaporization is boiling. There's two types, evaporation and boiling. We'll distinguish those two later on. And then we can see we're back to our last slope. So we have segment EF. So at this point, it is now all in the gaseous state. Delta T is increasing. Therefore, motion energy is increasing. Potential energy is going to remain constant. And phase change, there's none because it's now all in the gaseous state. So that's a heating curve. So there are 5 questions. Letter A, and these are off to the right of your graph. It asks, is this an endo or exothermic change? Well, you can see temperature increases, so that means it's absorbing. So this is an endothermic change. Letter B asks what phase is found at 80 degrees. Well, if I look at my graph and kind of extrapolate over, I intersect to segment CD. If I look at my table, that's the liquid state. So we find a liquid when that material is at 80 degrees Celsius. What is boiling point? So for letter C, what is the boiling point? So boiling again means a liquid changing to a gas. So that happened during segment DE. So if I extrapolate over, they already have that dashed line for us. that means 120 degrees Celsius. Make sure you include a unit because this can be in Celsius or Kelvin. What is the melting point? So when did it go through that phase change? That happened during segment BC. So again, extrapolate over, and that is 60 degrees Celsius. So that is a heating curve. Moving on, we have a cooling curve. So it's essentially the same thing. We can just see that we now have negative slopes. So starting out, we're at our highest temperature, and this graph is already labeled for us. So AB, think about what's at the highest temperature. We're just going to go in reverse. So this is going to be the gas. What's happening to delta T? It's decreasing. So if your temperature is going to slow down or decrease, that means your particles are going to start to slow down. So in cooling curves, the kinetic energy is starting to slow down. So that means particles will start to come together, get less space between them, and that's where we go through our exothermic changes. Potential energy, there's no potential energy being stored right now. It's all motion energy, and there's no phase change happening. We see these plateaus again, segment BC. In segment BC, this is where we have the gas liquid state, and I'm just going to abbreviate here, so G and L for gas and liquid. Temperature is remaining the same, so motion energy is the same. Potential energy is going to build up here. It's going to start to store that again. So what's it called, changing a gas to a liquid? That is our condensation point. Segment CD, we see a slope again, so we are now all the way into the liquid state. Delta T is decreasing, so again, we're slowing things down. Potential energy is going to remain constant here, no phase change taking place. In segment DE, this is where we're going to go through another phase change. We see that plateau, so we're going liquid to solid because we're decreasing temperature. Delta T is the same, so that means kinetic energy is remaining the same. It's going to increase that stored energy, and so at this point we're going from a liquid to a solid. That is called freezing. Our last segment, EF, we are now all the way in the solid state. Delta T continues to decrease, so motion energy continues to decrease. Nothing to worry about with potential. No phase change has taken place. We have 4 questions to answer, just like the previous graph. So is this endo or exothermic? Well, the system decreased temperature, so that means it lost heat to the surroundings. So heat exited, so this is exothermic. Again, just interpreting what phase is at 175. We've got to estimate here a little bit. So 175 looks like it would be about halfway between 150 and 200. So extrapolate over. AB is where the solid state is found. D asks condensing point. So what temperature is that at? That was again where segment BC was found. Follow it over. That's at 150 degrees Celsius. When does the substance freeze? So the liquid to solid change, that happened during segment DE. Extrapolate over, it's approximately 100 degrees Celsius. These are how you interpret heating and cooling curves.